Gno.key is the primary CLI tool for interacting with GNO chains. It handles key management, transaction signing, and querying. Let's explore the secure way to interact with gno.land by using Airgap Transaction and hardware keys. A transaction is any interaction with the blockchain. In local, you create an asymmetric key combined of one public and one private key. In local, using gno.key, you will create an asymmetric key composed of a public and a private key, and you will construct and sign the transaction using your private key. You will send alongside your signed transaction your public key that you will broadcast to the blockchain. If it is following the protocol, it will be added to the latest block of the blockchain. So in the end, why using a safe transaction? Gno.key is a non-custodial wallet, which means you're the only responsible of your wallet. In that case, it is secured by cryptography. For a bank, it will be secured by your ID. By being so, you are vulnerable to any attack on your laptop, which can be memory scrapping attacks, keyloggers, and so on. Being careful is not everything, because you can be vulnerable to the 0 days. A good protection will be to store your keys in an offline machine. You will construct and sign your transaction locally that will be returned to your online machine before being broadcast. To prevent any replay attack, you will send your public key to the blockchain that will return you your account ID and unknowns, which basically is a random number, which are gonna be sent to your offline machine. An evolution of the Airgap transaction is the hardware key. It is basically a specialized hardware that's made to store cryptographic keys. The private keys will never leave their secured environment. They will require physical confirmation to sign the local transactions. They are tamper resistant by design. They are also mostly immune to computer malware and are ergonomic due to their portability. So you will do basically the same thing than the Airgap transaction, at the opposite of the transaction details needed to be sent alongside the user authentication depending on the firmware of the hardware key. But by connecting our hardware key to our laptop, we are vulnerable to driver modification, which is uncommon but still possible. The last level is to build the two. You will do the same thing, but the keys never touch the network device because we are passing the information via a QR code. That's not everything because the information can still be modified on the online machine on the signed transaction. It has an advantages in securities, but it is less ergonomic, slower with complex setup. Even though you don't have exploit on the driver part, you still risk on the firmware. So it is not the perfect security. You must always verify your transaction details on the hardware key screens. The recommended solution today is to buy a hardware key because it is easy, secure, and convenient, and it proved itself in the last 10 years. As for Airgap environment, they are very accessible for anyone. They work with any offline machine. They don't need any specialized hardware, but that's the drawback. They don't have any specialized hardware, so they are less secure on that part. And they require for most of them multi-step process, which can be inconvenient. As I said before, the recommended way is to use a hardware key like Ledger, Trezor, and so on, which are on the way to be supported by gno.land. There is many other hardware keys, so I let you advise depending on your needs. If you want to go for an Airgap environment, which is secure but inconvenient, you can take an old smartphone, so of course disconnected of internet, or laptop, dedicated Raspberry Pi. You can take a USB key using Tails OS, which is an amnesic system. It resets with a permanent encrypted memory every time you restart it. It is very long to set up, so I highly recommend you to take a USB 3 if you take one. There's some application for iOS and Android, like I hope in the future Adena mobile. There's some possibility with MetaMask or Airgap application. A bonus if you do so is to use a dedicated profile with, I recommend, a secured alternative operating system like Graphene OS. It can be encrypted and disconnected from internet on that specific profile, so less risky to any malware. And for the very dedicated one on the laptop, there is CubeOS, which is a specialized operating system where basically every group of process has its own virtual machine, has gno.key, which can also be encrypted. It is taking a lot of RAM, but it is recommended for users with a very high risk. The good first step for anyone is to use a local password manager like KeePassXC. Honestly, it is only good to store your mnemonic, and the native way is with GNO key, which is vulnerable, but still very convenient and usable for low users. As for the mnemonic, never store your mnemonic in clear on network machine. It is always a good practice to encrypt it. So as I said before, with KeePassXC, which is the dedicated offline password manager. So as said before, you can use dedicated offline device for storing them, or you can trust it in a safe. The best practice for transaction safety is to always verify twice before signing, always verifying the recipient addresses, because the address can be spoofed and modified, they can be poisoned. When experimenting, never use your main keys. It is very easy to create a new keys, so take this as advantages. It is always a good practice to test periodically your recovery process, and you can store your mnemonic second hardware key in a fireproof safe at home, bank, or anything else. Alright, we did a big part. Now let's dig into the team management for keys signing. It's called multi-signature. Basically, let's say we have 3 participants all wanting to share one keys. Of course, it is not a good practice to share the same keys for everyone. Maybe we want to have a group decision before using the wallet. All the participants, Alice, Bob, and Charlie, will create a public and private keys, and they will send their public key to the key bases. A multi-sig key is created and sent to all of the 3 participants. Of course, it has to be done by one of the participants. And so the idea is like Alice can create a transaction that she will sign herself. She will ask Bob to sign it, and she will ask Charlie as well. And you can put a threshold like 2 out of 3 to use your signature. In that case, we set the threshold at 2. So if Bob or Charlie accept and they sign and send back the partial signature, she'll be able to combine the different signature and broadcast the final transactions. This process is essential in a company, for example. Now, let's say we have the exact opposite situation. We have one mnemonic we want to share for multiple people. It can be useful to hide very great your secrets. You split it in multiple shares that will reveal 0 information about the original secrets, and we can reconstruct with a threshold we set at the beginning. We only need 2 of the shares to create the reconstruct secrets. If you want to hide very great your original secrets, so like your mnemonic, you can give some of the shares to, let's say, family, for example, and by themselves they will be able to do nothing with it. But by asking this different information to these people you have trust in, even if some of the information has been destroyed, you'll be able to reconstruct the secret later on. As I say, it reveals nothing about the original secrets. You can add or revoke new shares without changing the secrets, which is very powerful. You can distribute shares across entities and locations, so for your friends or whatsoever. And you can even have a proof you have one part of the secret. Very simply, it can be seen like this, where we have a secret, we split it in 5 with 3 needed. We have the different secrets, and then we just put 3 of them and we have our result back. I finished explaining all the theoretical. Let's dip into the code part. To do a transaction, you put the key address, put in mode fast, you take the command, you copy, and you send it. Sometimes it works, sometimes there is not enough gas. But when it worked, I interacted with the blockchain. Our friends from Unblock created Adena wallet, which is basically a wallet you can use directly on the GNO web interface. We can just click on this little lightning and it will open this window we can approve. I've got some notification on the screen, and basically the transaction succeed. We have 2 nonce accounts, so the first one we registered and the second one with Adena. It is a very great and secure way to store your keys, but not as secure as an Airgap transaction. To do an Airgap transaction, you need to put the mode at full security, and you have multiple commands to execute. If we take back again our graph, this query lets you get the user authentications. So you put your public address, and this one is the node. This is the transaction we didn't broadcast yet. So to remember, the broadcast is -broadcast in the transactions. We then seen it with the result of the first query to avoid replace attack, and we replace the account number and the sequence number, and we broadcast it. Let's execute it. We set a valid address in the address field. We get this result with an account number of 0 and sequence 0. So this is quite unusual, but it's because we are in local environment. In real environment, you will get a random number in these 2 fields. Account number will be linked to your public keys, and sequence will be strictly random. Now we create the transaction. So this command should be done in a separate environment, like offline environment or hardware keys. So this created the call tx file, which is a big JSON. So let's sign it. Sequence number is equal to 0, account number is equal to 0, and address is equal to this string. TX has been saved and signed and rebroadcasted. I've got unlucky, I've got out of gas, but to avoid this situation, you have to put a little bit more gas than what you need, especially if it takes a bit of time. Even if you calculate the good number of gas, it's great to have a little security. This is especially useful in a multi-signature setup. Good thing we almost finished everything. I'm gonna preview the multisign-abc file that's being previewed in the issues. It can be found in this source I've took. It's a one file, so it's just executing everything. I'm just gonna show you the different steps, but basically it's what we saw earlier. We have the constant here, the public key, address, the key base. And so we initialize the three key base, so Alice, Bob, and Charlie's, made from the key base of the two others public key. Alice will take Bob and Charlie, Bob will take Alice, Charlie, and so on. We create a common transaction that should be signed in a payload. It's like the call tx file here. She generates the transaction signature. Note that each multisig participant used the account information of the multisig address. So these two numbers, the number and the sequence. So you must do query odds accounts with the address, exactly like we did earlier. Since Alice already signed the transaction, we ask now Bob to sign it. He generates a signature for himself, and then we combine the different signature. Alice signature we generate before, Bob's signature, and we set the key multisig ABC we created and directly broadcast. It's quite hard to explain more in details, but I recommend you to check these files I put in the repositories. I thank you for listening. All the sources as always are in descriptions. If you have any question, I'm available in the comment, and I see you next time.